Right. Okay. So this is the beginning of our contributed talks, and the first talk of today is given by Ram Fukaishi on productivity verification for functional programs. Thanks.
Hello. Let me start my presentation. And this talk is about automated verification for productivity for co-inductive data structures. Productivity is an essential property of co-inductive data structures. And co-inductive data structure is, in general, infinite data structure, such as infinite lists, also known as streams and infinite trees. Productivity means that each element of the data structure can be generated eventually. For example, the first line defines infinite lists consisting of infinitely many ones. And this is a productive definition. But the second line is not productive because the head function requires that S has already generated at least one element, but it doesn't. So the element of the second stream are never produced. And we proposed a new productivity verification method by reduction from productivity to termination. I'll consider more tricky examples, which we call left tree and right tree. The definition of the left tree is here. Node is the constructor of the binary tree, and left is the destructor, which retrieves the left child. Left tree is not productive because we can't generate the left child. Let's try to generate the left child. We can unfold the left T, and we can price the destructor left, but it coincides with the original term, so we can't generate the left child. As a result, left tree represents a non-productive tree in this figure. Next, the definition of the right tree is here. Right is the destructor for right child. And on the contrary, we can generate the left child of right tree. We can unfold the left T. We can apply the destructor right. We can unfold the left T again. Then we can calculate the label of the left child as 1. So right tree represents a productive tree in this figure. Let me discuss some related work. One of the main approaches for productivity verification was type-based. Type-based method counts the number of constructors and destructors. For example, the left T inside the definition of the left tree is applied one destructor left and one constructor node. Since the numbers are same, the type-based approach rejects this definition. And this is fine because left tree is indeed non-productive. But it also rejects the definition of right tree, although it is actually productive. So previous type methods is too conservative. The productivity of term writing system is also studied. For example, Andrew et al. Proposed a reduction from productivity to context-sensitive termination. But the approach can't use an ordinary termination checker. Also, the approach doesn't directly support higher order functions. And this is the outline of the rest of my presentation. Let me overview our method. Our approach is reduction from productivity to termination. We consider a functional program with co-inductive data structures as a source program. Given a source program that generates a co-inductive data structure, we translate it into a function which takes a path which represents a position of the data structure and returns the corresponding element. So the target program no longer has co-inductive data structure, and a co-inductive data structure in the source program is productive just if the translated program is terminating. So we can use off-the-shelf termination checker and non-termination checker for productivity verification. As I said, we translate a co-inductive data structure into a function which takes a path and returns a corresponding element. A path is represented by a sequence of destructors or integer list. I'll explain it by using an example of a binary tree. We first regard a path as a sequence of destructors, and we can get corresponding elements by applying the destructors left to right. We can also regard a path as an integer list by converting destructor into an integer. In this case, projection 0 is converted into an integer 0, and projection 1 is converted into 1. Then we can consider a co-inductive data structure as a function like this. In this way, we translate a co-inductive data structure into a function. I'll introduce a detailed idea of the translation through the examples of left tree and right tree. Left tree is translated into this recursive function t. Here, the constructor node is translated into this function. It takes a tuple consisting of the function L corresponding to the left child, and label x, and the function R corresponding to the right child. Then it takes an integer list as a path and perform pattern matching on it. If the argument is null, it returns the label x. If the list starts from 0, it refers to the component of the left child, so it passes to the passes the remaining path ls dash to the function L. If the list starts from 1, it refers to the right component, so it passes the remaining path to the R. Otherwise, the argument list doesn't represent any position of the data structure, so it returns the meaningless value 0. The destructor left is translated into this function. It extends the path by integer 0. And we can verify the termination, the non-termination of the function t. So our method can verify the non-productivity of the left tree. And similarly, right tree is translated into this recursive function. The destructor right is translated into a function that extends the argument ls and passes to the function corresponding to the parent. And we can verify the termination of the function by a termination checker. So our method can verify the productivity of such an example. Now let me sketch formal definitions of the source language and target language and the translation. Our source language is called by name random calculus with co-inductive types. The non-functional type denoted by sigma includes integers, products, sum, and recursive types. A co-inductive type is represented by a fixed point type denoted by nu. For example, the type of stream is represented by this, and the type of binary tree is represented by this. The type denoted by tau is either a non-functional data type or function type. So we do not allow functions stored in co-inductive data structures. The term denoted by M is those of standard lambda calculus with fixed points. And the recursive definition of co-inductive data structure is represented by using a fixed point operator. For example, a right tree explained before is represented by this term. Now let me explain the definition of productivity. We define a term n of type sigma as productive if for every pulse gamma to access an element, gamma m is terminating. Here, gamma m denotes the term obtained by applying the corresponding destructors. For example, a stream m is productive if and only if these terms are terminating. And it is equivalent to the statement that for every I, the ith element can be calculated eventually. The target language for our reduction from productivity to termination is also called by name lambda calculus, but it doesn't contain co-inductive data because they are translated into functions. Instead, the target language has primitives on integer list so that we can express paths. The terms of the target language contains primitives on integer lists such as new, cons, and pattern matching on lists. Our translation is type-directed translation. The judgment of the translation is quadruple relation. Gamma is the type environment, and M is the original program, and tau is the type of M, and N is the translated program. Let's consider an example here. Suppose X is a variable of stream type. Pi0x represents the head of the stream X. It is translated into a function like this. This function returns the first element of the stream if the argument u is null list. I'll introduce some translation rules. Lambda abstractions and applications are translated recursively like this. A pair is translated into a function as a constructor node. If the argument u is null, it returns the label of the pair constructor, and it is a default value 0. And the first element of the u is 0. It refers to the component of the left child. So it passes the remaining path u dash to n0 obtained from in m0. If the list starts from 1, similarly, it passes the remaining path U dash to N1. A projection is translated into a function as in the destructors left and right. Now I explain the correctness of the translation. Our translation is sound and complete. The theorem states that the original program M is productive if and only if the translated program N is terminating for all input list. Due to the soundness and completeness, we can verify not only productivity but also non-productivity via termination and non-termination checker. Then I'll talk about implementation and experimental results. As I said, productivity and non-productivity are reduced to the termination and non-termination problems. We implemented a new termination checker because there's no termination checker that supports integer list primitives and whose performance is sufficient. The termination and non-termination problems are further reduced to the validity problem of higher order fixed point logic, for short HFL. HFL handles higher order predicates and fixed point operators. We generate two formulas that correspond to termination and non-termination. There is a HFL solver named mu-HFL that can handle integer primitives. We extended mu-HFL with integer lists. As a result, we can check productivity and non-productivity in this scheme. We conducted experiments on this table. We used mainly our original benchmark. And this column shows the time for verifying productivity or non-productivity. And this column shows whether the size type system can prove productivity. The table contains right tree and left tree explained before. It also contains a Fibonacci stream as a higher order case. TI ranges over natural numbers, instances that are productive if and only if I is even number. So our tool can verify, our tool successfully verified all test cases except T1 and T38. So our tool can verify some instances that previous tools can't handle. But the performance is low in some cases. First, the performance for refutation, such as left tree and T1, is low because our non-termination checker can't find counterexample efficiently. Second, the performance for higher order case is also low. The improvement for these cases is our future work. Let me conclude my presentation. We have proposed a method for reducing productivity to termination verification for functional programs without co-inductive types and proved its correctness. We also implemented a prototype productivity checker based on our method and conducted experiments. Then we confirmed the effectiveness of our method for some instances that previous tools can't handle. In future work, we aim to support other properties such as safety and liveness. We also implement our productivity checker for actual programming languages like Haskell. Thank you for listening.
Now we have time for a couple of questions.
there are no other questions. So you define the notion of productivity in terms of termination. And then, to me, it's not a surprise to get then at the end a sound and a completeness result. If you have defined the notion of productivity according to another property, then what you would expect, again, a sound and completeness results? Do you see my question? If you put up the slides on productivity, when you define it in terms of termination.
Actually, we can define productivity as convergence into infinite term, but we can't we can't directly handle such terms, so we define productivity by termination.
It was just the answer to your question to the man's, I don't know your name. Alberto. So suppose that I have an interpreter for some programming language, and I enumerate a tree that contains all of the possible input for this interpreter, and then I if-map my interpreter onto it, and then I ask whether or not this the procedure that produces this tree is productive, right? And then certainly I cannot, right? So it's so I suppose you will get undecidability for this reason alone.
Put up the slide on productivity. And can you put up that slide? When you define it, you could have chosen, this is a research topic, so to speak, you could have chosen another definition of productivity in terms of another property, not termination, and see how this relationship between productivity and this other property could be defined.
So I can actually answer because I've worked on similar problems in the past, and usually at least what we did is we define productivity semantically as, because it's a co-inductive definition, so we define it as the final coalgebra of some functor, and then using about the objects in this final coalgebra. And if these objects are finite, infinite trees, then your term is productive.